Hello, everybody. I hope all of you are well and healthy. In this short video, I would like to explain how we can write a simple assembly hello world program using two different techniques. So I have created a folder in here called hello world. And in this folder, I created two other subfolder named method1 and method2. So I will be uploading this into Canvas so that you guys can access these two different techniques as your reference when you want to write programs. All right, let's first go to method one and see what we have there. In method one, we have our hello world.asm, and then we have this object file that was created automatically and this binary file that was created automatically before. So I remove them for now because we don't need them at this point. And then what I have here, there are two files, hello world.sm, and there's a shell file here. I will be explaining about the shell file later. Now just let's focus on the .asm file. Let's use Vim and go to the file and see what is in there. So I've given a brief comment in here. Before going to this code, please take a look at the document that I have uploaded in Canvas. It's called Linux System Call. Basically, the way that assembly programs deal with input and output devices in your computer is kind of different from high-level programming languages. Those access through high-level programming languages done automatically when you invoke a syntax. But in assembly, you need to set and configure all the corresponding registers to access the I/O peripheral. And so by this, I mean that when you write the code, you only have access to the CPU. If you want to access the input and output peripheral, then this is the system kernel, it's the Linux kernel that does that for you. You cannot access it. You request access from a Linux kernel, and Linux kernel then, based on the register that you configure, it make those resources available to you. So one of those peripheral is the keyboard. Keyboard is the STD-in or a standard input peripheral. And the other one that we are using mostly in this course is the standard output, which is your monitor, your desktop monitor or your laptop monitor. So when we want to print out something on the printer, on the monitor, and when we want to read something from the keyboard, we need to configure some register in the CPU. And then once we configure those registers in the CPU, then we can ask the kernel to come and fulfill our request. Linux kernel take a look at those registers and then do the process accordingly. All right, now let's take a look at the structure of the program. So basically, this is our program that's only for hello world. So we have two sections here, section data and section text. In the data part, we put our data, initialized or uninitialized data. So this is where you store your variable, your string, or you declare your variable, that uninitialized variable that later on you can be used. You can use them. And then there is the section .text here where your main code goes. If you want to compare this with C, this is where you declare your variable like integer A, integer B, char C, string something, right? And this section is like after your main function. All right, let's start here. Take a look what we have here. All right, in here we basically declare a message variable defined as a byte, and we say hello world, and then we have 0xa, 0xt. 0xa is like a /n in C, meaning like new line, and 0xt is the carriage variable. So it means that it's a return variable. So once it's the message print out from on the screen, when you use 0xt, it's gonna go to the beginning of the line. And when you have 0a, it's like a /n. So once the message print out on the screen, then by seeing 0xa, which the decimal value is 10, your cursor gonna go to the next line. So this message is a label that's gonna be at one point in the memory. So we're gonna be defining a memory location with label message where this data are gonna go and be stored in that location. And then we have the message length. Basically, it's specified the length of hello world in there. So there are two ways to do that. You can directly count the length of the message and declare the message length like this, message length equal 14, for example, or you can let the system do that automatically for you, counting the number of characters. So the way that we do it is we say message length is equal to dollar minus message. Meaning that dollar implies the location of memory at the current time, and message is the label that we defined before. So it means that the current location at memory at this time is some value like X, and the location of the memory at message and that at message label was at the beginning of that memory. Therefore, if you deduct the current location from the message label, it gives you the length of your message. So if you are confused with this, you can directly specify the length of your message and use this second command line. But later on, once you get more advanced in this course, then you can use this kind of command to tell what the length of your message in the memory is. And that system is going to be doing that for you automatically. Okay, we only have this data, so we put this data in the memory, and then let's see how we can print it on the screen. So here is the section.x, it is where our code goes. So we declare a label like underscore start. All of our assembly program should have this label in it. And then it's like a main label in C program. And then we start the main program. What we do, we start configuring some registers, and then we call the Linux kernel to print out that message for us. So to do that, we have to put 4 into EAX register. This is a system call for write command. So when you want to write something on the screen, you have to populate EAX register with number 4. And then when you want to tell, okay, you want to write this, but where we want to write this? We want to write it on the screen, or we want to write this on an LCD, or we want to write it on a file. So different I/O has different number associated with it. So for monitor or a standard output, the number is 1. So 1 you put in EAX register so that the system understands that you're going to write on the screen. And then, okay, so you want to write and you want to write on the screen. So what do you want to write on the screen? So you have to tell the system. You specify that with this. You put the label in the memory into ECX register. You give that variable and populate ECX with that variable name. Now the system knows that it has to write something, and it has to write it on the screen, and it has to go to the memory and look for a place called message. Okay, now it knows that where it has to fetch the data, but it doesn't know how many data or how many character has to fetch. Next register, EDX register, tells the system the length of the message. So here is the message length. We populate EDX register with the length of the message. So the system goes and take a look at the EDX register and see, okay, it has to take 14 character. Now it knows where to write. It knows that has to write, and you know where to write it, and it knows where to get the message from, and it knows how many characters should get from the memory. And now once we are done with the configuration, then we call the Linux kernel. So how we call it? Using this command, interrupt 80 hex. So interrupt 80 hex is a number for Linux kernel. Once you call it, it's gonna call the Linux kernel. Linux kernel is gonna take a look at those registers, do the processing accordingly, and then come back here. So it goes there and print out the message on the screen for you, and then it comes back. The control gonna go to the next line. The next line again is a system call. Why? From here we can understand, okay, we are again calling the Linux kernel, but what we have in those registers, we have 1 in EAX and we have 0 in EBX value. 1 in EX register tells the system, okay, we're done with it and we want to exit the program. And then in order to understand whether the message, whether the process has been completed successfully or not, you put 0 value in EBX register, and later on you can verify that. If you reach to this point, it means that your program completed until this point successfully. So this is only for information purposes for you, that your program has been completed successfully until this point. And then you have integer interrupt 80 hex. So this is, you populated those registers, and then you call the system kernel, and system kernel gonna exit from the program, and your program at this point is complete. All right, this is all the program we have, all the code that we have in this file. So we just exit it, and then let's see how we can run this program. Okay, how we can run this? First off, we have to create the object file. To create the object file, we say basically nazem -f, and my object file format is elf, and then the name of the assembly file, for which this case is hello world 1.asm. So once we do that, then object file is created for us, and here's the object file. The next step is linking the object file as explained in lecture 3. So for linking, we say ld -m elf i386, and then the name of the object file, which is hello world.o. So once we say this, then we're gonna get our binary file, which is a.out. At this point, we can run our binary file and see if the program is running well. Yes, it's running well. So hello world is printed out in here. One thing else that I want to mention is that you can also specify the name of your output file. If you want to do that, you use this -o option to tell the program that you want to choose a name for your binary. In here, I choose the name hello. Okay. So if I list down again my output, you're going to be seeing a hello file at this point. Now I can run this hello and see what happened. All right, so we are getting the same result as before. All right, we run the program, and as you can see, I had several Linux commands to create the object file, and also for linking process and running the file. So what I did in here, I create a shell file run1.sh to automate this process. Let's see what is inside run1.sh. So as you can see here, I have nasm -f, meaning that the format is ELF, and $1.sm, which is $1 is the first argument of my shell command that I will be showing you in a second. And then I link those files with the libraries. So it is the syntax that I show you in the lecture slide, and then at the end I run the binary. So let's get out of the file and see how we can use this command. So we say run.sh and then the name of the assembly file. But remember that you shouldn't be adding the extension name, because this is the way that I wrote the program. If you add the extension name, it won't work. So I do that, so you see that the message is printed out successfully in here. In this course, you can practice writing your own shell file to automate the compiling and linking and running process in a single file, put it in a single file and then run it, so that you don't need to repeat the process if you have to update your file and or for debugging purposes when you are doing this process over and over. So this is going to save you a lot of time. Okay, so as I said, I created two different methods for the Hello World program. So this is method 1. So let's go to method 2. In method 2, I use the technique that I have explained in lecture 3. Basically, we're gonna be using the mix of the C file and assembly file and use the textbook macro to facilitate our assembly code writing and debugging. So let's see how this makes our job, how this could make our job of writing code easier. So you are all familiar from that lecture. So these are the files that we need to make this, to use those macro. So once you are planning to use those macro, make sure that you have all these files. Okay, in here, I created hello world.asm file. This is my main assembly file that I have to write my code in. In lecture 3 and lab 3, I provided you the skill.asm file where you can write your assembly code in that file and run it, where you can also use the macro from the textbook. So let's take a look at the Hello World 2, see what is inside. Okay, I have it open in here. All right, this is my Hello World file, but this time I'm gonna be using the macro from the textbook. So this is the macro from textbook. Print a string. Print a string gonna be is the syntax that prints out a string of character on the standard output which is the monitor for you. So this is the skeleton that I provided. So these are not something that you need to write. So this is provided to you. This is the only code that we needed to have for Hello World program. I just define a message label in the memory and put that message label in the memory, and then I assign that label to EAX register and then call print string command, and I'm done. So as simple as this. So the macro from the textbook gonna be helping us a lot. Here is one example of those situations. So we have different macros defined in the textbook for us that can do different things. We can print an integer on the screen. We can read an integer from the keyboard. We can dump the value of the registers within a code when we are for debugging purposes. So many things that we can do with this textbook macro. And here is one of the examples. Let's see how we can run this code. So as explained in lecture 3, we have a lot of syntaxes for creating the object file from the C and assembly file. You can see here we have C file, and then we have include file, we have assembly file in here. And for each of these, we have to create the object file and then link them together. In lecture 3, we said that we can automate this process using a shell file. And this is how we do it. So we first create an object file from asm.io.asm, and then we create the object file from driver.c, and then we create object file from our hello world program. As we said that hello world going to be in an argument for the shell command. So when it takes it, going to be replaced with this $1. And then we have our linking. So we said that GCC can link all these object files for you automatically. Okay, I have a typo in here, so it has to be driver.o because we're gonna be linking all the object file. And finally, we run the binary. All right, so let's save it and then go to the process. You say run.sh and then the name of your main file, in our case, hello world 2. So when we say this, you can see that hello world is printed out on the screen. As you can see in these two technique, in these two methods, we use shell scripting to automate the process. And I recommend you guys follow this to make your job easier for debugging, and it's gonna saving your time a lot. Thank you for listening.